Hello, welcome back to our machine design series where today we are talking about fracture mechanics. So linear elastic fracture mechanics is a theory that we can use to describe a brittle failure mode of both brittle and ductile materials. So keep in mind that so-called ductile materials can still experience this brittle failure mode, and the reason for that is that all materials have these small defects inside. So in linear elastic fracture mechanics, we say, okay, these little defects, they can propagate in size, they can grow in size under load until eventually our cross-section is no longer able to handle the load that's on it, and we experience sudden failure. So with linear elastic fracture mechanics, we are today going to talk about this static type of load failure, and really what we'll be talking about is the stress intensity factors associated with fracture. And then we will compare that to fracture toughness. Okay, so that's a material property, and we'll discuss what that material property depends on, and actually it turns out it depends on a lot of different things to do with the material. And then we will wrap it up by talking about a safety factor that you can use to predict whether your part is going to be damage resistant or not. And when I say damage resistant, of course I mean whether or not we predict that a defect inside your material of a particular size is going to cause a fracture type of failure in your material. All right, so I've got a couple demonstrations ready for today, so we'll be back on camera in a little bit, but for now, let's get started. So as we said, sudden brittle fracture of ductile materials can occur, and as a designer, we need to be aware of this possibility, and we're going to use linear elastic fracture mechanics as a theory to predict the behavior of these cracks in materials under stress. So let me write all that out. All right, so let's get started with this theory. We are going to start by looking at an infinite plate that is loaded with a uniaxial tensile stress. So you can think of this as like our dog bone sample, and then we're going to introduce a little flaw in the middle of it. All right, here's our diagram of our infinite plate. So I've drawn it as kind of a blob with an oval in the middle, but that blob just means that we can imagine it extends on forever, right? This is a giant plate with a small elliptical defect in the middle of it. Okay, and we're loading it on top and bottom with a uniaxial stress, sigma, and that stress, sigma, at the corners A and negative A, so we're looking at the corner here and the corner here, that stress is going to be higher than the nominal stress, or the far field stress is what we would call it. It's going to be higher at these corners than it is everywhere else in the material. And that's because we can think of these load lines, right? So if I have a load line on the end over here, it would just be coming like straight up and down. But as I come in, my load line has to kind of conform around the edge of my defect, and it'll do the same thing over here, and that leads to a stress concentration, right? Okay, so we've got these hot spots in the corners, and I'm not gonna bore you with the whole derivation, but I'm just gonna tell you that that maximum stress is in the y direction, right? It's a uniaxial tension in the y direction, so that maximum sigma y is equal to 1 plus 2 times a over b, where a over b are the dimensions of that ellipse, times sigma, the nominal or far field stress. Something interesting, and maybe this will just help with understanding the magnitude of this amplitude of stress. So if we have a circular crack instead of an ellipse, or circular defect instead of an ellipse, then A is equal to B, right? So if A is equal to B, then this ratio here is going to be equal to 1, and that means that my maximum, sigma y, is 3 times the nominal. So it's a significant amplification of the stress, right? And if we have an ellipse, then that actually amplifies it more, right? The ratio of A over B is going to be higher because A is going to be greater than B, and so we can get stresses in that corner that are very large. Actually, let me move over to a quick demonstration so we can see what this actually looks like. All right, so here's a demonstration. This is what we're really talking about, right? So imagine that this piece of paper is actually a piece of steel or whatever your part might be, and it would, of course, also be much bigger than this. If we're talking about an infinite plate, it extends on to infinity. But the point, nevertheless, is that the stress concentrations are going to be located at these corners. Okay, so when I pull on this thing, I'm going to do my best to do a uniform axial pull here. I'm going to expect to see that the braking is going to initiate at these corners. So let's see if that's true. It takes a lot of force. Look at that. Perfect tear begins right here. You can sort of see that. Oop, I'm tearing it more. But now once the tear is started, it'll be a little bit easier to keep it going. All right, so we got total failure there, and it started at each of the two corners. It started at this corner first, but then eventually also traveled over to this corner. So this is what we're talking about. The stresses at these two corners are higher than anywhere else in the material. So if we're going to get a fracture, then we'd expect it to start at those corners first. All right, so now we've seen what that looks like. Let's move on to something a little bit more complicated. So in this example, we are conceptualizing that we might be able to see the dimension B. We might be able to actually see the height of the crack. But in practical applications, it might not be possible to measure the height of the crack. We may only see a sliver, so we'll have the length, but we might not be able to see that height. And so what can we do in that situation? Well, let's first just see what this equation gives us. Let's say we have a microscopically fine crack. So B is approaching 0. And when B approaches 0, what does that do to our maximum stress in this equation? Try to work it out for a minute. If you're thinking that it leads to an infinite stress, you are correct. So our maximum stress approaches infinity. Now, of course, this is impossible. We will not have an infinitely sharp crack, so B will never be exactly equal to 0. It's never going to be infinitesimally small. And this observation of the fact that this is physically impossible inspired the work from Griffith. He sort of is the father of the field of linear elastic fracture mechanics. And Irwin then expanded this work by introducing what we call the stress intensity factor. And this is what we're going to spend the rest of today talking about. Okay, so we've introduced here the stress intensity factor, and it's given by this equation K1 equals sigma times the square root of pi a. And this is for a mode 1 crack in an infinite plate. Okay, so the mode 1, this is indicated by that subscript, Roman numeral 1 in front of K. And we'll talk about what that means in a minute. But first, let's define the other terms. So sigma and A, these are essentially the same dimensions and stress is what we have labeled up here, except for now we're talking about a crack that is small so that this B dimension has approached 0. So we're still talking about the half length of the crack, so the full length of the crack would be 2 times A, and the far field stress sigma is what we're applying at the ends. Okay, so let's see first what that looks like, and then we will talk about the different modes of crack propagation. Okay, so here was our initial demonstration. We had this elliptical shaped crack, and we said that the stress concentrations were at these corners. Okay, so now let's take a look at an infinitesimally small crack, or infinitesimally narrow crack. So I still have the same length of 2A, but you can't even see actually that there's a crack in here, although I can promise you that I did cut this. Maybe if I do it like this, you can sort of see. There's a cut here, right? Okay, but it is very narrow, and so we're not going to be able to measure what the height of this thing is. But we do know that we're still going to have stress concentrations at the edges. And it's not going to be infinity, right? Because if I put a load on here, I can pull this apart and it's not cracking, or tearing. So that means that our stresses at the ends are not infinity when I put any kind of load on this. I still have to achieve some sort of stress or reach some threshold, or what we would call a critical stress intensity. So I have to reach a critical stress intensity at these edges in order for it to ultimately tear. And that stress intensity, K1, is what we've just defined. So if I pull on this thing hard enough, let's make sure it still tears at the edges. It does, right? So we can see that we still have a maximum stress at these corners. That's where our crack starts on both edges, but it's not equal to infinity. So we need some other way to think about this. And we're back. Okay, so there are 3 distinct crack propagation modes that we'll talk about, and those are opening, sliding, and tearing. All right, so mode 1 is an opening mode. We have a tensile stress that's acting normal or perpendicular to the plane of the crack. And then in mode 2, we have in-plane shear. This is a sliding mode. So we have a shear stress that's acting parallel to the plane of the crack. And finally, mode 3 is our tearing mode. And for our tearing mode, we have a shear stress that's acting parallel to the plane of the crack and parallel to the crack front. So here's our crack front. Right, our crack front is this line here, so we're parallel to this, and we're also acting in the plane of the crack for tearing. All right, so I have set up here a demonstration for each of the 3 distinct crack propagation modes. So let's start off with mode 1. Mode 1 is the opening mode. This is the mode that we've already seen so far, and I have the arrows pointing in the direction of the load for mode 1. So this is crack opening. So I've introduced a small crack here on the edge that's size A. And if I apply enough of a tensile stress, then a crack will propagate from this corner through my cross section. That's mode 1. Mode 2. Mode 2 is a sliding mode, and I've drawn arrows again in the direction of the load or the stress that should be applied. So I'm gonna push to the left here, and I'm gonna push to the right down here. We'll see if I can do this. Do it this way. This is going to be really difficult. It folds a lot. Let's see. Hard to keep it from tearing. There we go. Okay, so there we go. We got a sliding mode, although I'm not sure that was pure sliding. In any case, hopefully that demonstrates the concept that in a sliding mode, we have sort of a shearing force, one going, one sliding in one direction, one sliding the other. Okay, mode 3 is a tearing mode. And so these arrows, if you've forgotten, the cross represents going into the page, the point represents coming out of the page. And again, I've introduced a small crack here. And so this is the easiest way to tear a piece of paper, right? If I push down here and I pull up on this side, I can easily tear through this piece of paper. Okay, so those are the three modes, and for this class, we're just going to focus on mode 1. It's the most common mode, and often the most important. So now let's return to our conversation about the stress intensity factor. So that stress intensity factor, K1, is a function of geometry, size, and shape of the crack, and the type of loading, depending on whether it's mode 1, mode 2, or mode 3. So for a particular load and geometry configuration, we can modify this original equation that we had, where this equation is just good for the mode 1 crack in an infinite plate, so just a crack inside of an infinite plate. We can modify that, though, for many different geometries. All right, so here's our modified stress intensity factor for mode 1. We have introduced this factor beta, which is our stress intensity modification factor. And beta is going to depend on your type of loading and the configuration of your geometry. So for example, our previous equation just worked for a infinitesimally small crack inside of an infinite plate, right? But let's say that we have a circular rod, maybe we have a tie rod, or maybe we have a connecting rod inside of your engine, and it's just this cylindrical rod, but it's got a little nick in the side of it, maybe just a penny-shaped kind of crack. We can modify our stress intensity factor equation to account for that difference in geometry as compared to an infinite plate with a small crack using this equation. And there are many different configurations that very intelligent people have worked out. Very good researchers have worked out, and some of those can be found in your textbook, and then there are more in the literature. If you want a really good reference, you can look at the text by Tada and Paris. I'll put the full reference in the description, but this is a really thick textbook. It's maybe like this thick, full of different stress intensity modification factors. All right, so that's how we find our stress intensity factor for our particular loading scenario. Now we need something to compare that stress intensity factor to understand when we predict failure. So we're going to use a critical stress intensity factor, and we're going to say when our stress intensity factor K1 reaches a critical value, K1C, crack propagation initiates. All right, and this K1C is called the critical stress intensity factor. Sometimes it's also referred to as the fracture toughness of the material. And that material property depends on a few things. First of all, of course, it depends on the material. Do we have a steel? Do we have an aluminum? And what kinds of heat treatments have been applied to that material. Those factors all matter when it comes to the critical stress intensity factor, or fracture toughness. It also depends on the crack mode. So K1 K1C is different from K2C, is different from K3C. So depending on which mode, opening, sliding, or tearing, that you're looking at. It also depends on the processing of the material. I already mentioned that. But yes, heat treatment matters. And any other processing that's been done on the material matters. The temperature matters. We know that materials behave in more of a brittle manner at lower temperatures. So if you have a very low temperature application, then fracture mechanics should become more of a concern at lower temperatures. Loading rate also matters. And the state of stress. At the crack site. So it does matter whether you have plane stress, plane strain, or a triaxial stress state, and it matters what the magnitude of those stresses in each dimension are. Alright, so if you have a material that has a reported fracture toughness, you need to understand all of these different factors that went into measuring that fracture toughness and make sure that they're consistent with your application. And if they're not, which in many cases they're not because it depends on so many different factors, then you may want to consider doing some of your own fracture toughness testing. Okay. So now let's say you know your fracture toughness or your critical stress intensity factor K1C, and we've analyzed our loading situation. We know K1. We can write a pretty simple factor of safety. Our factor of safety is just the ratio of our fracture toughness to our stress intensity K1. Okay, and this is analogous to other safety factors that we've seen, right? We're taking our material property and our upper limit of what our material can withstand, dividing it by our particular stress state, our particular scenario, to see how close we are to that upper limit. All right, so that's going to wrap us up on an introduction to fracture mechanics. So we learned about the different modes of crack propagation. We saw some demonstrations of how the stress intensity works. I want you to keep in mind through all of linear elastic fracture mechanics that when we're talking about a higher stress at these corners here that I've highlighted, even when we're talking about a higher stress where our height B has gone down to 0 for an infinitely small crack or microscopically fine crack, the stress that is amplified at those corners, that is not just because we have a reduced cross-section. Okay, this is a different concept entirely, and it comes from the energy release rate, which we won't delve into here, but it has a different foundation entirely from the type of stresses that we've calculated so far. Okay, so we're not just talking about the difference in having a cross-sectional area that extends all the way across versus a cross-sectional area where we've taken out some material. Okay, so that's a different concept entirely. Here we're talking about the stress being amplified at the corners because of the discontinuity, because we have a defect, a crack. So in this infinite plate, right, if we take out a little bit of material, it's still close to infinitely wide. This cross-section is still close to infinitely large. So we're not talking about a change in cross-section. We are talking about a change in geometry. We're talking about a concentration of stress at an edge, at a defect. And really what we're talking about is the change in surface energy that it takes to propagate a crack. So the energy that it takes to actually form two new surfaces. But again, not going to get too deep into the energy release rate discussion here. I just wanted to make that point that this is different from what we've seen before. All right, and so once we are able to calculate a stress intensity factor and we're able to measure or are given a fracture toughness, then we can calculate a factor of safety to understand how damage tolerant our design is. All right, that brings us to a close on our introduction to fracture mechanics, and with it, a close to the final chapter in preventing failure under static loading. We started this series with the basics: stress, strain, material properties, and in this playlist, we worked our way through ductile and brittle failure theories, and now fracture mechanics. So what's the takeaway? Even in static loading, materials can fail in ways that aren't obvious from the outside. It's not just about the maximum stress. Geometry, defects, material properties, and processing all matter. A component can be under its allowable stress and still fail catastrophically if a crack is lurking somewhere. Understanding these principles is not just an academic exercise. This is what helps engineers design safer, stronger, and more reliable products. Coming up next, we are going to shift gears into fatigue loading, where time and loading will bring new challenges to the table. Until then, keep questioning your assumptions, keep double-checking your stress calculations, and most importantly, keep designing like failure is not an option. Thank you for watching. Don't forget to like and subscribe and share if this helped you out, and I will see you in the next one.